the retrieved document are those documents which have the similar property with the given query. Class, am I audible? No?
Yeah, ma'am, you are.
Because there is because there is internet issue, so please inform me if I am not audible.
Yeah, sure, ma'am. Will ping you.
Okay. Okay. So that are some different kind of search engines. Now, we'll see what are the different possible kind of search engines you will find in your like like search operation. Okay, so one is like in library catalog. If you try to perform any search operation, then how you perform the search? You provide keyword, or in more detail way, if you want to perform the search operation, then you will perform the search operation using title, author, and maybe sometime you will provide the code related to that book or something. So that is very conventional way of performing the search operation. Means that is the search engine which is very conventional. Okay, second one is like text based. So like in Google, Yahoo, all these search engine, you provide your query in form of text. Like it can be a keyword, it can be a single word, or it can be a phrase. Okay, so, and the third one is a type of image based. Okay, so now we all know that you can provide image for performing the search operation. So their shape, their color can be considered for the means search properties. And here keyword can be extracted from the caption of the image. Okay, so in this way image based search operation can be performed. Now you have one ask.com website which provide you the facility of question answering type of search operation. Okay, now we have seen that clustering type of search engine you have sometime, like this Clusty and VVCMO. So what they do, if you have words, if you have a particular word, so they will try to cluster them according to their similar meaning. Means according to their semantic property, they try to create the cluster of the words. Okay, so suppose if you want to perform the search for word jaguar, so jaguar can be a car, can be an animal, or maybe belong to some other cluster also. So when you are going to search with this keyword jaguar, then your search engine will return the result in the form of all these all these documents. Okay, means it will generate the result from the animal cluster also, and from the car cluster also, right? So in this way clustering systems can be used for search operation. Now some very common type of queries which generally people ask is like how to get rid of stretch marks, and sometime only single word can be used for performing the search operation. And just look at the second last word, interstellar trailer. So here, by adding this trailer word, you are providing the keyword, means you are specifying the query. If you only provide interstellar, then it will provide all the information, maybe from the interstellar, and maybe from the movie domain, means all the information will be provided. But if you have added trailer after the interstellar, then it will provide information related to the movie domain only. Okay, so in that way you can more specifically provide the query. Now the size of the indexed World Wide Web can be seen like So the data which is provided here is taken in 2014. Like 45, about 45 billion pages indexed by Google. Okay, and about 25 billion pages are indexed by Bing. Right, so they are huge, and since it was taken only in 2014 and it's 2021, so you can see how much it has grown up, right? Now Twitter hits 400 million tweets per day, so that was given in 2012. So for more detail you can check for the current status, what is the current per day tweets. Okay, now 2.5 billion photos uploaded to YouTube each month in 2010. See, it's actually exponentially growing. Okay, here you can see that the data are okay. So to process that data, how to extract the information from such a huge data set, so that is a challenge. Okay, so yeah, so challenges, again same thing what I have told you, that how you can extract the relevant document from the given this big data. Okay, now so we'll see that how we can solve that. But before that, let's see the characteristics of user queries. Characteristic means what type of queries do user post on the internet. So they usually in the form of sessions. User ask, so sometimes when multiple time for a same website, then under that web page they will write the session information, that you have visiting it fourth time in this month or something like that. Okay, so that is the session information. So user ask one query and then they come back and revisit it later because they are still interested in the same topic. Okay, so that is contained in the same session. Okay, and then sometimes queries are very short, maybe just of 2 words long, maybe or just 1 word. So that is different characteristics of the queries. And sometimes while performing the search operation, the query contain lot of typological errors, and a small number of popular queries means sometimes people ask that kind of search, means sometimes people perform that kind of search operation, that type of queries which are never asked. So means that is what for searching relevant document for that kind of queries is again a challenging task. Okay, and almost no use of advanced query operators. That means even though search engine provides advanced query operators such as like word one near to word two, or word one is immediately adjacent to word two, and or operators, okay, and colon operators, most users don't use those operators except for phrases which users have learned. Okay, means generally user pass the query in terms of phrases, though they don't use any operators, right? So because they are not aware that they can even perform any operators while performing the search operation, right? So this is the characteristics of the user queries. Now information retrieval is a very important process that involves a collection of documents and a user query. And the goal of this process is to find the relevant documents that match the user's query. So this is all about information retrieval. Now, the Key terms used in information retrievals are query, document, collection, index, and term. So we'll see one by one. Query is a representation of what the user is looking for, okay, and it can be a list of words or a phrase. And document is an information entity that the user want to retrieve. Okay, so means query is the search text, and document is the retrieved, means in which document you found the query word. Okay, so and it means your document does not have to be a single web page. It can be a passage or it can be an entire website. Okay, so that need to be remembered. And collection is a set of documents, and index is a representation of information that makes query means querying easier. So index is also a very important term. And now term is word or concept that appears in a document of or a query. So we will see most of the time we are going to use these terminologies. Okay, so documents are not just printed paper. It can be a record, pages, website, images, people, movies, anything. Okay, and they are often encoded in many different formats. So there has to be some process that converts them into some standard representation form. For example, Unicode. Okay, and documents have to be represented internally in the computer. Okay, in the computer, and they have to be pre-processed. They have to be pre-processed. Example, removing metadata and removing JavaScript, right? And documents include words, terms, typos, tokens. So what is this type here? Type means it is just a set of all the occurrences of the same word. Same means different occurrence of the same word is representing the type, and token is every particular instance of that particular word. So this is the difference between type and tokens. Now search engine architecture means how your search engine looks like. So we first have to decide what we want to index, and then we have to collect that information. Further, we have to index it efficiently and then keep the index up to date. This is the task of the search engine, right? Means you have to perform the indexing. What was the index? We have seen that a representation of information that makes querying easier. Okay, so this is the task. So here, once we have built the index, we have to make sure to provide a user friendly query. Okay, means the query is not should in the form of like very typical words, or it is following any formula or anything. It should be in natural language form, and natural language form is nothing but user friendly query. Now this is the architecture uh, of search engine, how search operation performed. So here you can see very new words like document collector, document collection, and here that side you have query. So one side you have means half of this diagram include document information, and half means right side of this diagram include query information. Okay, so we have our information source here in this diagram. You can see in the document collector. Okay, you can see here document collector. This information is going to the information collector, and that creates a document collection. Then we have a document processor. You can see here document processor, and that converts the document into an index. So now you got how the document is converted into index form, because directly document cannot be stored, no, so they are converted into Unicode format, and then they have provided some indexing. Now on the other side we have a query that gets processed by the query processor. You can see that, and this query processor is used to perform a query representation, and then there are mapping between document and the queries to a process called document ranking. Okay, this document ranking perform the mapping between the query and the document. Okay, and which processes the input document, find which one are similar to the user's query, and it returns search result. You can see here, uh, let me use the marker. So here you can see that uh, this is the search result. Okay, so uh, so this search result are then shown to the user. You can see that are shown to the user using this search interface. This search interface is nothing but, if you try to relate this entire process with your search engine, suppose you are using your Google. So your Google output is nothing but the search interface here. Okay, then the user looks at those documents and decides which one are relevant and which one are not, and then possibly revise their information need. It will revise its information need and starting with a completely new query. Right, this is what we all do. So sometimes we search for something, and by looking at the result we feel that no, this is not required, we need to perform some new query. So that is this thing. Otherwise what we think, no, our query was okay, but we need to revise it, we need to update the query. So that can be done through this side. So user can perform two type of tasks, like it can either completely update the query or it can revise the query. Okay, so that's all from the search engine architecture. And after that, how we can represent the document. So document can be represented in term document matrix form. So term, we have seen that term can be a word or a phrase. So generally term is representing a word. Okay, so term document matrix can be, if terms are m and documents are n, then matrix size is going to be m cross n. Otherwise, document can be represented with document matrix. So size is going to be n cross n. So suppose if the document is 3 million and terms are 50,000. So you can assume what is, how big is the size. So actually this is representing a medium sized collection. This is not the big one, this is the medium size. And typical example on the web is like when n is 30 billion and m is um, 1 million. Okay, so in that case this is the super big size of the data set. Okay, now how, what is this boolean and integer value matrices? So since here you can see that we are going to represent the document in the form of matrix. So if the values inside the matrix are in boolean form, boolean means 0 or 1 form, then this just says there that the specific term appears in that particular document or not. Okay, if 0, then that term is not present in that current document. if one that particular term is appeared uh, in that document. Okay. Otherwise, what was who is that? Suman Kumar.
Yeah, he's a part of the CSC group only. I think he is joining from other mail
Uh,
ID.
yeah. Actually, yeah. So actually, I think it is not allowed in this Zoom meeting. Sorry, in this Google Meet. So tell him to join with the other Miss Institute ID. Okay.
Okay, man.
Okay. Yeah. So we were discussing about Boolean and now integer valued matrix. So what is integer valued matrix? When the values are um, means it is not just 0 or 1, it can be any other value. So what these values are representing actually, how many times that term is appearing in that document. Okay, suppose if the value in the matrix is 5, so that means that particular term is appearing 5 times in that particular document. Okay, so the values inside the matrix can be in the boolean form or in the integer valued form. Now, we have seen that if you have a medium sized collection, then how big is your matrix is going to be. Okay, and is there any way to do better? Means, do we need all this information? Because here we have seen that in Boolean matrix, values either going to be 0 or 1. So most of the time, means 50% of this matrix is going to include 0. So that means that 0 values are what? Irrelevant. We don't need that information. We want when the value is non-zero, because that is going to provide you some information, right? So by this representation, means with this matrix representation, we are not going to get uh, means we are not utilizing the space properly. So storage issues were there. So that is solved by this inverted index form. So instead of an incidence vector, use a posting table. So that means the previous one is represented as incidence vector, and now in the current slide we are discussing about posting table. So this posting table means for each term, you need to include only those documents in which they are appearing. No need to include those documents in which they are not appearing. Like, for example, Vermont. So Vermont appear in 3 documents only, D1, D2, and D6. Whereas Massachusetts appear in D1, D5, D6, and D7. Okay, so whereas in case of the previous representation, they include the dimension of the vector in this representation is going to be of length n, whereas in this case it is not fixed. It depends on the documents in which they are appearing. So for this kind of representation, linked list is used. Okay, so here we need to use linked list to be able to insert new document, order, and to remove existing posting. So suppose means in case of linked list representation, we all know that insertion and right. So from document D2. So deleting D2 from the linked list is easy. Then then performing this operation in array or matrix, right? So how many times that document is occurring, and it keeps everything sorted. Yeah. So one thing is also here that for each term or for each word, the documents need to be sorted. logarithmic, right? Now, there are some basic operations which can be performed on this inverted index. So what are the operation? Conjunction, disjunction, negation, recursive operation, optimization. We have two, we include both of these words, right? So and operation means when we have all the operation. Okay, so voice is not clear.
Yeah, ma'am. I think
Okay,
it
so
is.
let me reconnect. Okay, let me reconnect.
Okay, ma'am.
Okay, am I audible now?
Yes, ma'am.
Okay. So we were discussing about the basic operation that can be performed on inverted indexes. So first one is conjunction operation, which is nothing but AND operator. So AND operator means all the condition need to be satisfied for getting the output, for getting the positive output, right? So suppose we have two words and we want to find which document include both of these words. That means we need to perform AND operator, and that is going to take big O x plus y complexity. X plus y is the length, x is representing length of first document and y is representing length of y document. Okay, so the complexity is addition of all these length of all these documents. And disjunction or operator uh, means suppose you have two words, we want to find those document in which means which include any of these word. Okay, similarly negation, like we want, suppose we are searching for word one and we want that second word is not present. Okay, so that kind of information also can be retrieved. So all that thing can be performed in inverted indexes. Now, other main topic of this information retrieval is vector space model, VSM, vector space model. So actually documents are typically represented in the vector space model. Okay, so here um, you can see we have three-dimensional space, right?
Cosine similarity.
Yeah, cosine similarity, yes. So we will reach there, but before that, this is representing three-dimensional space. So each dimension is representing terms here, like T1, T2, T3 are nothing but terms. Term 1, term 2, term 3, and they are representing each dimension. So that means we can have an n dimensional space that has the different terms like 1, 2, 3 until n. And then each of the document is represented as a vector in that vector space. So here D1, D2, D3 are what? Documents. And these documents are represented with vector form in this vector space model. So in this way, we represent terms and documents in the vector space model. Okay. Now, yeah, one more thing I wanted to explain here. Here, yeah, as I have already told that terms can be like word. And suppose, just take an example. The terms are cat, dog, and elephant. Okay, and the documents are linear combination of vectors along the axis. Okay, so a document that contains for example, three instance of cat, one instance of word, because document, no, we know document is nothing but a complete information, means it is like full of information. It can be in the form of paragraph or something like that. So that means suppose you have a document that include three instance of cat, one instance of word dog, and one instance of word elephant. Then what would be the vector representation here? So vector representation is 311, because first word was cat and that appeared three times. Second word was dog and that appears one time. And third word was elephant and which appears one time. So vector representation for that document is 311. Okay, in this three-dimensional space. So in this way we represent terms and documents. We will see some examples. Okay, now document similarity. So now we have represented them in n-dimensional space. Now how we can find the similarity, means the similarity between the document and the query. This is the main task. So actually it is used in information retrieval to determine which document is more similar to a given query queue. So in the given diagram you can see that you have two documents d1 d2, and you have one query queue. Okay, so here you need to note that the document and queries are represented in the same space, same dimensional, same means two-dimensional space. Okay, and the angle between two vectors is used as a proxy for the similarity of the underlying documents. Okay, so here angle is used for finding the similarity. So for example, the similarity between D1 and Q, means document 1 and query Q, is proportional to the angle alpha between these two vectors. Is it clear? And the similarity between document 2 and query Q is represented, is actually is a proportional to theta, angle theta between these two vectors. Okay, and a slightly better version of the similarities is based on the cosine of that angle. Means if you directly consider that angle, that does not mean anything. So actually you need to take the cosine of that angle. So this is what Anirudh was telling, that cosine similarity. This is also called as not just document similarity, it is known as cosine similarity. Okay, so this is actually a cosine of alpha versus cosine of theta, and then in this quadrant they related in the same direction. You can see that here they are aligned in the same direction because they are in the same quadrant. Okay, so that means if the cosine is smaller, what does that mean? The angle is also smaller, which leads to the larger similarity. Okay, so how you can find the similarity? If the cosine similarity is small, means they are inversely proportional, means similarity between the document and the query is large if the cosine similarity is small, right? So the formula is given here. Uh, so the cosine measure is computed as the normalized dot product of two vectors. So sigma D is document, Q is query, and so here what is DI? So DI is the ith component of vector D. I'm talking about this DI, right? And here you have QI. So QI is what? Ith component of query Q. So you have to simply multiply them, and then you have to take the linear combination of them, and then you need to divide them with the length of the document and their square root, and the length of the query and their square root. Okay. And there is one more variant of cosine is the Jacob coefficient. So formula is given here. Okay. So let's see one example for finding the cosine similarity between the given document and the query. So suppose you have one document, this one. Okay. So document is cat, dog, dog. So and their corresponding vector is 1, 2, 0. How it is? Because it is three dimensional, we are going to represent them in three dimensional space. That's why we have taken the vector value as 3, right? 3 vector values means the dimension, means the length of the vector is 3. So first dimension is representing cat, second dimension is representing dog, and third dimension is representing mouse. Okay. So um, how many times your cat is occurring in the document? One time. That's why this one is here. And dog is appearing 2 times, and mouse is appearing 0 times in the document. And the query is cat, dog, mouse, right? So cat is appearing 1 time, dog is appearing 1 time, mouse is appearing 2 times. So that's how you are representing your query in the vector form. Now for the cosine similarity, the formula is this one. So you have to multiply each component, and then you need to take the addition, means linear combination of them. Okay, so after solving this values, you got the cosine similarity as 0.55. That means there is only 55% similarity between means this query and the document. And one more thing we have done here, we have performed the we wanted to find the cosine similarity between the vector with itself. So we have seen that the similarity is 1. Definitely, if you try to compare the vector with itself only, so you are going to get the maximum similarity, right? So the maximum value of the cosine similarity is 1. So that you got from here. So what is the minimum similarity then? Can you think of minimum? Okay, so let's think of some other examples. Suppose you have given 3 documents, D1, D2, and D3, and all have dimension 2. You can see here the dimension of all these documents is 2 only. So uh, so for the first for the first document, the vector value is 1 and 3. Second vector value is 10 and 30, and for the third one, values are 3 and 1. So can you find any relation between these vectors? Means all these vector values means 1, 3, 10, 30, 3, 1. Can you find the relation? Okay, so actually the question is compute the cosine scores for D1 and D2. Means what is the similarity between document D1 and D2. So without computation, can you tell their score just by looking at their vector values? Any idea? Can you think of just they are just means the second document vector value is just the scaled version of the first one, isn't it? Just multiply 1 with 10, you will get this one. Multiply 3 with 10, you will get this one. So the second document is nothing but just the scaled version of the first one. So we have seen that in the means this is what 2D representation. So in 2D representation, this D1 and D2 are nothing but they are in the same direction and in the same quadrant, and actually they are representing same document only, but the second one is the scaled version. So the for that reason, the angle between these two vectors are 0. So we know that when the cosine value is smaller, at that time the similarity is maximum. So that's why the similarity between these two is 1. Whereas when you will try to check between D1 and D2, similarity is going to be minimum because they are inverse. They are opposite of each other. Means uh, 1 3, the vector is 1 3, here it is 3 1. Okay, it means if you are trying to discuss in terms of mathematics, so they are inverse of each other. And if you try to apply the formula, and you will see that you are going to get the minimum similarity, cosine similarity between them. Okay, so just by looking at the vector values, you can also assume their similarity values. Okay, so you can see here, um, so it is not 0 between D1 and D3, it is around 0.6. Okay, because their vector values are swapped. And in the first one, D1 and D2, one of the two documents is a scaled version of the other. Okay, so that's why the and so for analyzing the result and the mathematics, you can apply this formula. You can apply this formula and evaluate the answer. Okay. Now, what is the range of values that the cosine score can take? So we have seen that maximum value can be 1, but what about the minimum value? So minimum can be 0 or -1. That depends on the size of the vector. Okay, in general, the cosine function has a range of -1 to 1. However, when the two vectors are both in the first quadrant, right? If they are in the first quadrant, then the range is 0 to 1. Okay, now let's discuss about distributional similarity. Okay, so two words that appear in similar context are likely to be semantically related. So, I want to I went to a search engine and search for name of words that appear together with word drive. Okay, so I performed a search for name of words that appear with the word drive. So what I got: schedule or test drive and investigate Honda's financing options. Second, Volkswagen debuted a new version of its front wheel drive Golf. The third one is the Jeep reminded me of a recent drive. And the last one, our test drive took place at the wheel of loaded front EL model. So what you can understand from here? Is my search operation performed efficiently? So you can see that the word drive appears in all those sentences, and a name of a car also appears in them. You can see that, no? Drive is present in all these documents along with one car. Okay, so that means Honda, Volkswagen, Jeep, Ford are related to each other. They all are related to each other, and because they appear all near to the word drive. Okay, that's why they appear with word drive, no? So this is what distributional similarity. Okay, so one thing more you can think of: the context of the word in which they are appearing. So context can be like the word before the target word, the word after the target word, the word within end words of the target word. Okay, and the word within the same sentence, the word within the same document. So these are the context of the target word. Okay, so because in case of distributional similarity, we are trying to see the what is the definition here? Two words that appear in similar context are likely to be semantically related. So that's why we need to understand what is the context also. Okay. So here we have discussed today. So yeah, that is the end of the lecture. And today we have discussed about information retrieval. What is information retrieval? How it is important? What are the challenges? And after that, what is the architecture? What is the basic architecture of this search operation? And yeah, document representation and vector space model. Okay, that is very important. Vector space model, you may get some numerical on this one. Okay, document similarity means cosine similarity, everything. Okay, so yeah, this was the main topic which I have completed. And in the next lecture, I'm going to discuss about principal component analysis. Because again, in this one, we are representing document. Now, we are representing document with a vector. Where is that? We are representing document in the vector form. Now, so sometime, because here in this case in this example, the document size as well as the query size was very small. So in this case there is no problem, but in real case the vector size is huge. So how we can reduce this vector dimension? So for that we need to study principal component analysis, which is actually used for feature dimension reduction. Okay, so this is very important technique actually. So I thought you must have completed this in machine learning, but it was not. So I will discuss it. Okay, the next lecture. Okay, so yeah. Yeah, thank you everyone. We can leave now.
Okay, ma'am.
Yeah.